Alright, so if you just come in, please could you head over to menti.com, use that code. Just 3 questions, just checking the basics of the course so far.
We had tropical fish in a strip, but I was upset because I thought the white people were fast because they're in grass. And then we put the fish in place. But it was a small tropical fish. Yeah, because then the bubble was grass. Well, I was but I refused. In the grass.
No, I don't know what's... The connection is not great.
Morning.
Hello, so just doing a little check-in. Yes.
Gymnastics. You know what I mean. Well, turning is a very different verb in English.
I turned in gymnastics. Well, actually I didn't because I was always scared. That's why I quit. At some point I ran like around, around like a rod, you have to like circle around, and I was way too scared to do that, so I quit.
I know exactly what you mean.
And then I started doing cycles, and now I'm here.
No. Career switch.
Oh my god, damn, am I late as well? Like, you also live further. Yeah. Annoying, right?
Alright. So, yeah, if you haven't just give me some feedback so far. Basically what I'm doing is checking in now that there is nothing egregiously wrong with the course that I can change right now that will make it much better. Yeah. So I just want a heads up if there's something I should be doing or should not be doing that is completely ruining the course for you, let me know. If I can change it, I will. Alright, so SOC, alright. Okay, so I will read over all of this, and do what I can. Keep filling in if you're still doing that, but I'm going to switch over to the iPad, and hopefully we'll stop having. Hey, okay. All right, I'm also trying a different recording scheme, so I hope it works. I've got my little webcam, which will hopefully record a bit better than the previous one, and I'm going to stop at 45 minutes and restart the recording program so that I don't get a missed gap like we had last time. All right, so I will be putting up the dates for the midterm today. I just had an email from OSA saying they can sort that out, so you'll know about the midterm. It is in week 4. I'm trying to decide if we should have it during the tutorial or later in the evening. Is there a general view here? Tell me what you think.
What day would it be?
It depends. So also if you have a day preference. I mean, if it's in the tutorial, obviously it'll be on the Thursday.
Yeah, just not Monday.
No, that'd be crazy. So it would, I mean, if it's in the evening, I think it would run from 5:15 until 7:15.
I'd rather not.
Yeah,
Okay.
just do it during the tutorial.
Early morning though.
All right, let's.
Unless dinner is provided.
I'm fine with 5.
That's
Unless you provide dinner. But
I mean, yeah, that is always the problem with the, yeah. All right, I'll try and keep it in the tutorial. So,
supper.
yeah, but let me confirm once I've had a chat with Osa. All right, so, what is on the menu for today? Well, on the menu for today, we are carrying on. Oh, would you mind just just flip the little switchy thing? Thank you. Or if not, just leave it, it's fine. So we're carrying on with curves and parameterizations. Hopefully the stuff that we did in the tutorials on Thursday was helpful there, so that when we look at it today in 3 dimensions, the whole curves and parameterization isn't quite so crazy as it was at the end of last lecture. Then we move on to functions of several variables. So what we dealt with last week was a function where we took in a single variable, time in this case, and spat out a vector. Now we're thinking about what happens if you take in a whole bunch of variables. And it should be no surprise that we do what we always do as soon as we get a new kind of function. We want to think about derivatives. So we're going to do a little bit on limits and continuity. I just want you to have seen it, so that at some point in your life, when someone says, "Did you see it?" you can say yes. And if you go into more serious kind of physics and stuff where you're actually having to work with limits and continuity, you kind of know where in the textbook to go and find out about it. But we're not going to do epsilon delta proofs. Yay! Yay! You want epsilon delta proofs?
yes.
Okay, I can give you some. If you want them, ask me. I'd be delighted. Okay, so that's going to allow us to get to partial derivatives, not derivatives like you know and love from in 1 dimension. As you'll see, we have to do something a little different. So we'll get to partial derivatives. Of course, once we've taken one derivative, we're going to want to take more derivatives. So we get higher order derivatives, which we've seen before. We're just kind of extending ideas now. Of course, we're going to do the chain rule. So this is really stuff that you have a lot of intuition about, just extending it. And then finally, we're going to get to the kind of the new thing and a lot of the notation that we need in order to carry on and do things like Maxwell's equations. Okay. All right. So curves and parameterizations. So now you hopefully have a better feel for what it is to parameterize a curve. And we are now thinking in 3 dimensions. So we've got a particle moving through space over time. So we want to know, if I give you the time 2 seconds, where is our particle? And the best way that we can do this is to describe the position of our particle where each component in our x, y, and z is a function of time. Okay, so that we've seen. This is to give you an intuition, but you don't have to have that this is time. You can parameterize with whatever scalar you like, okay, whatever makes sense for you. So you might end up parameterizing with angle if you're working, say, in a spherical coordinate system or something like that. So you can play this game with any kind of little parameter here that you like, but if you're wanting to kind of get it in your head as an intuition, think of it as time. All right, so I can't remember, did we look through this example last week? Okay, so let's talk through this. As you see, I've put the solution up, so that's a bit of a spoiler alert. All right, but let's think about what it is that we're doing here. So we've got a plane, and we've got a paraboloid. Okay, so you've got some plane doing something, and you've got a paraboloid like this. And if you imagine how they might intersect, we want to think about they're going to intersect if you've got a plane, you've got a parabola, they're going to intersect in some curve. And we would like to parameterize that curve. How do we do that? Well, the annoying thing about parameterization, there's no absolute formula that you can follow that will tell you how to parameterize. You need to kind of do it a lot and screw up a lot and kind of get an intuition for it, and then life gets better. But it's worth thinking, what is it that we want to do when we want to parameterize? We want to parameterize, we want to find functions x of t, y of t, and z of t, so that this thingy here, this vector here, moves us along the parabola that is the intersection of these two surfaces. That's what we're trying to do. Okay, well, we get told, because this is a starting problem, that t is equal to x. So that kind of gives us a hint as to how to start our parameterization. So you won't always be told how to start it off. Sometimes you will have to figure out how to start it off. But here we've got t is equal to x. Okay, so let's plug that in. Well, if we plug that x is equal to t, we can plug that into the plane equation. So now we know that y is equal to 1 minus t. So that was pretty straightforward. Okay, and now you can plug that into your equation for z, and you get z as a function of t. And so you end up with a parameterization that looks like this. So this just says that if you let t go from minus infinity to infinity, this position will map out the intersection of those two curves. Questions? Comments?
Could you repeat the last thing again?
What it,
Yeah.
okay, so what we found here, so okay, think about what we're doing. We've got some plane, and I've got a paraboloid. I don't know exactly how it looks, but if you can think about the intersection, it's going to be a curve. And what I want to do is create a function that when I let t change, as t changes, it moves along that intersection. And that's what this does.
Okay.
Yeah?
Yeah.
Okay. So again, I'm going to do a little bit of sweeping stuff under the rug here. As you can imagine, with functions of one variable, you had some weird things that had like points and discontinuities, and those made things like taking derivatives and stuff complicated. Well, you can imagine if you've got surfaces, you could have weird stuff as well. You could have holes, you could have points, things like that. But just like for most of calculus of one dimension, or calculus of one variable, you mostly dealt with nice smooth curves that didn't do anything weird. We're going to assume that we're going to deal with nice, mostly smooth surfaces that don't do anything weird, so that we don't have to deal with pathological cases, pointy bits, asymptotes, things like that. So that's a kind of one thing to think about. You can think a little bit more about, so you learned with derivatives that the first derivative not existing can mean that there's a break or that there's a point. When we talk about derivatives here, you can think about what that means for your surfaces. But mostly we'll just assume that everything's fluffy and there are unicorns and it's all lovely. Okay, so that's the one thing. The other thing is the frustrating thing with let me try it again. It's not even like I drank a lot for Halloween. Parameterization is not unique. So one thing to check for yourself is that these three things, which all look quite different, actually give you exactly the same curve. It can be a good thing, it can be a bad thing. So what is the curve that these parameterize? Anyone want to take a guess?
Circle.
Circle. Okay, so if you were feeling a bit hazy about that, go back and check the worksheets from last week. Yeah. All right. All right. So a couple of things, just words you need to know about curves. So suppose we have a curve, okay, and it starts at some time t equals a, and it does its little curvy thing, and it stops at time t equals b. All right. It's closed if where we start and where we end up are the same point. No surprises there. Pretty good name. Okay. It's non-self-intersecting if there's nowhere where it kind of crosses over itself. So if there are no places where there are two different times where it has the same value. If you imagine this curve over here, as it comes along here, there'll be some time when it reaches that point, and then sometime later it goes through exactly the same point. If it doesn't do that, it's non-self-intersecting. And mostly we will deal with non-self-intersecting curves because they make life easier. And mostly, in fact, what we will deal with is non-self-intersecting closed curves, which we just call simple closed curves. Just nice little things that start at one point, do their thing, and go back to one point, and they don't intersect. Okay. All right. So, here's a pretty common or garden kind of question. We want to parameterize the curve of intersection of this plane and an elliptic cylinder. Okay, so what's an elliptic cylinder? Okay, what's a cylinder?
Like a can.
Like a can. Okay, so something you're thinking something like this. Okay, so if it's an elliptic cylinder, what do you think you can tell about it?
It's just like a normal cylinder, but instead of like the top being circle, it's knobs.
Yes. So you usually, I mean, we're used to from school having circular cylinders. We don't even call them right circular cylinders, we just call them cylinders. But cylinders can have any cross section. If this has an elliptic cross section, it's an elliptic cylinder. Okay, so if you think about what we've got, this cylinder, is it like this? So is it up and down the z-axis, along the y-axis, or along the x-axis?
Z on the Z-axis.
How do you know?
Like Z is free, so you can kind of replicate it at every level of Z.
Right, so you know that basically you've got x squared plus 4y squared equals 4, which is an ellipse, and that's happening at every single z value. Okay, so we've got our cylinder like so, and we've got a plane doing something. Okay, I'm not going to ask you to visualize that because I can't visualize that. Okay, but we've got a plane, it's like cutting it like so, it's cutting it like so, it's doing something. Okay, so if you visualize this, what do you think that the curve of intersection will look like?
Kind of like an ellipse.
Okay, kind of ellipse-ish. All right.
Stretched in some way.
But stretched, depending on whatever. I mean, it would be an exact ellipse if we were cutting it like. Okay. All right. So that gives us an idea. So, thinking about what you learned on Thursday, how might you begin parameterizing this?
You add x in terms of t. And
Okay.
then y in terms of x with the new t parameter.
Okay. And because we're dealing with an ellipse, do you have an idea of a function you could use? So how last week did we parameterize things like circles and ellipses?
Cosine and sine.
Yeah.
Ah, awesome. Okay. So, if it was a circle, what would we use? If it was a circle, we just use cos and sine with no, with some parameter, some amplitude to get the radius. Okay, we need to be a little trixier because we've got an ellipse here. So we're going to want, so I'm going to have my x of t. So I'm thinking about actually parameterizing this ellipse for the moment, and then we'll get it in the right form in a moment. So I'm going to have my x of t and my y of t. You don't have to do, you could have gone the other direction, you could have used your cos and sine in the other way, but I'm going to do this. And I need to think about, if I want to be mapping out points on that cylinder, what amplitudes do I need?
I think it's 2 and 1. So 2 for cosine and 1 for sine.
Okay, let's check it. Does this work? And how did you guess that?
Well, because if you put in x in the formula, right, then you get 2 cosine t squared, which is 4 cosine squared t.
Mm-hmm.
And then you get, because the 4 times sine squared of t
Nice.
And then you kind of factor them, and it becomes 1. And yeah.
Cool. Okay. So if this is going a bit fast, please work through the worksheets from last tutorial. But yeah. Okay. So we've actually got our first bit of parameterization done, because now we're moving on this cylinder, but using t. So any t that we put in here is going to give us a point on that cylinder. And we pick any z. And okay, so the final thing we need to do is just pick out those points. So this at the moment is just a parameterization of the cylinder, and z would be free. But now we actually need to pick out the points specifically on the plane, and the way that we do that is just like we always do when we intersect things. We plug these values for x and y into our equation for the plane, and that will give us z in terms of t. So let's just do that.
Just one question.
Yeah.
Parameterized y from the beginning here, but in the other examples you derived y after parameterizing x.
Sorry, there's no rule. So I mean, here it's done like this because, I mean, in a sense it is derived from this. As soon as I say I'm going to use cosine of t, you could figure out that I needed y to be that.
Okay, so you just did it intuitively, but you would have, in theory, have to put x in and then find out what y is, and it would be some cos squared 1 minus sine squared and come to that conclusion. Okay.
Yeah. But the thing to kind of create a little memory hook is if you're ever dealing with a circle, your parameterization is probably going to be x of t equals radius cosine of t, y of t is going to be radius sine of t, and if you're dealing with an ellipse, then you have this where you figure out what the major, semi-major, and minor axes are. Okay. All right. So if we plug those in, what do we get? I will let you double check. Okay. So you do your z. You'll get z is equal to 1. Okay. Let me just write down the final answer. Okay, so what I would like you to do for homework is to go through and check that you're happy plugging those two in and ending up here, and then think about what it is that you've actually got. So now what you've got is for every value of t that you put in between 0 and 2 pi, you are going to map out a point on the intersection of your cylinder and your curve. And I highly recommend using something like GeoGebra to actually plot the cylinder, plot the plane, and then plot the curve and just check that you got it right. Okay. All right, so far we've been thinking of our parameterization as time or something arbitrary, but one of the very useful parameterizations that we can use is we can parameterize in terms of arc length. So we're actually parameterizing by how far along the curve we've gone, which is going to be super useful if we want to know the length of the curve. Okay, so that's what we're looking at now. So what are the things that we're going to think about? We're going to think about, we're not dealing with closed curves at the moment, but this is going to apply there as well. But we are just thinking about a bounded, so it has a start and it has a finish, continuous curve, no breaks or jumps. It's going to be nice and smooth, and it's non-intersecting. And we're going to have it specified in terms of t for the moment. And what we're going to do, like we always do when we're trying to deal with curves, is we're going to break it up into straight lines that we can actually deal with. So we imagine that we just kind of put a few points on the curve, and then we join each point with a segment. Okay? So far so good. So this is what I just said, but in fancy maths. Okay? We pick a bunch of times, which gives us points on the curves, and then we connect straight lines between those points on the curves. Okay, so this is our curve. Our curve is being divided into n arcs, and we use the chord length, which is the absolute value. So notice now, suddenly, we can start to use our vector notation. So I'm thinking of each of these as a position in space given to me by a vector. And so if I subtract the two and take their magnitude, that gives me the magnitude of that chord length. So that's what's happening over here. And I add up the lengths of all those little straight lines. So that's all that's happening here. I'm adding up. And you can imagine that the smaller I made my little chords, the closer I'd get to a good approximation. Okay? This should all be feeling very familiar. You've done this thing in different ways. That's why I'm not going in a lot of detail. All right. The one thing you will notice, because you've got a curve like so, and you're taking chords in between points, and the curve will actually go around, you are always getting an underestimate by this method. And by changing and by increasing the number of points that you look at, and maybe wiggling them around, you can get closer and closer to the actual thing, but you will never go over. So we can find a lower bound. We can find a smallest number such that any sum of those little chords is less than or equal to that thing. And if you have a nicely behaved curve, in fact, you can define that this S is the length of the chord. Okay. This is just to give you a feel for what we're doing. It should feel intuitive. You don't need to do any crazy calculations with this. Those are reserved for here. Okay, so how can we quantify what it is that we're doing? Well, we're writing our change in time as a delta t, and all we've really done here is, I mean, what we had, if you think back, we had this, which we have is really Sn is equal to what I'm calling my delta r here. I am just doing a delta t times a delta t, I mean a delta t over delta t, so I'm just multiplying by 1. Okay, so I'm not actually changing the formula, I'm just doing this because it's actually going to be useful, and then I rewrite it, and I just put some absolute value signs in. But this is the same formula, this is just summing up the little bits. Okay, but then I can do my usual magic calculus thing and go, okay, I'm going to make delta t really small, I'm going to take my deltas and make them d's, I'm going to take my delta t and make it a dt, and bazinga, I have an integral. Okay. If you want to be more pure mathsy, please ask me, I'll be happy to go through this, give you exercises and stuff. But what we take out of all of this is now we have an equation for calculating the length of a curve. Okay, because remember, this is the length of our curve, right? We do the limit, I think I should have an equal sign in there. So we've got this thing over here, but we know that dr by dt is just our velocity, our first derivative of our position vector. So we've got our speed, so here we're really just integrating our speed along the distance that we went, and we get the length, which is kind of exactly what we would expect. So it's kind of nice. Okay, so that's arc length, and it is a parameterization, and it's a parameterization that gets used a lot. And you do need to be able to calculate arc lengths, because we're going to need them later on in the course. Okay, so just to clarify, our arc length element for our curve, so we're thinking that you're used to having like a dx or a dy, which is just like a little element. Well, our arc length element is called ds, and you can work it out like so. And if you want to find your curve, we integrate along our little arc length elements, which is the same as integrating from start to end of the velocity. All right, so here you go. We've got some curve, y equals f of x. The first thing I'd like you to do is think about how do you find our arc length. So I'm keeping it really simple. What I want to know is, I know that like dx looks like that, and I know that dy looks like that. I want to find ds in terms of x and f of x, or x and y. So I'm going to work through this because I think it will hopefully pull together what we're talking about. All right, so let's think about this in terms of what we've been doing so far. So the first thing is we need a position vector, because everything we talked about has a position vector. And because we're just in 2 dimensions, we've got that our position vector r, well, since I'm dealing with f of x, I'm going to think of r as a function of x. Okay. Previously we were thinking of r as a function of t because we were in 3 dimensions, but I'm thinking of my parameter now as x. So this will be a little head twisty, but let's go for it. Alright, so I want to write a point on my line using my vector notation, so using my little unit vectors. What will the coordinates of this point be? X and f of x, right? So I will just have an x here and an f of x there. Okay. So this is hopefully pulling it together into the 2-dimensional stuff that you know, the 3-dimensional stuff that might be a bit weird. Okay, well, we know that in order to find anything to do with the arc length, we need the velocity, which is the derivative. So I need v of x. Don't feel like you have to bring in time. This is a notional velocity. It's the derivative with respect to the parameter. So it's the derivative with respect to x. Okay? Yes, I am messing with you. Yes, I'm doing it on purpose. Okay? Because this will happen more and more. It's one of the things that really frustrates me with mathematicians and textbooks. They like to think that they're so rigorous and like they keep the notation the same and everything, but they really don't. Like x's and t's get muddled up, like used for the same thing, and it just messes with everyone's heads. So yeah, best thing is to get used to it. Okay, how do I take the derivative of this bunny with respect to x? Derivative of this, which is just 1, so that's an I hat. And derivative of f of x, so I'm just going to write that as df by dx, j hat. Okay, so my velocity is I hat plus this bit. Okay, so from the, yeah?
I'm wondering, what's the difference between the velocity that's v of x and v of x that is a vector?
The difference is a lecturer who forgot the hat.
You're supposed to have that, right?
I'm supposed to have the hat, yeah.
And why is it a hat? Or why is
Is
it
it,
a vector?
well, is it supposed to be? Sorry, no, it should just be a parameter. You're right. I shouldn't have those. I'm just so used to writing x hats at the moment. Okay, that's better. No hats, no arrows. Okay, thank you. Good catch. Okay. All right, but we know that we just showed that our arc length is. We go back here. Is this thing. All right, so if we plug in what we've got, this is going to be the absolute value of our I hat plus f prime x j hat. If we actually work this out, because this is just the length of that little vector, what do we get? We get And this might actually look familiar to you. It's the arc length formula in one dimension, on a one-dimensional curve. Anyone seen it before? Okay, well, so this is just to show you, if this does look familiar, that everything that you learnt about arc length when you were dealing with functions of one variable actually falls out of the more variable system. You can do this with vectors. Okay. Alright, so I'm going to leave this because this is pretty straightforward now. Okay, so now you know the tricks. Alright, you're here, you're given the position vector, you're asked to find the length of the curve for this. Well, you know that you're going to integrate your arc length element, you know how to find your arc length element. What do we need? Okay, hands up if you want me to do this. Alright, we'll do it. Okay, so we want to find the length of the curve. So our position at some time t equals -1 of our little fly starts here, it does some buzzy thing according to this until time t equals 2, and then it stops, and we want to know how far it traveled. Okay, well, we have a formula for this. Okay, so in order to find this, we are going to need our velocity. So now we are parameterized in terms of t, so we can think of this as a prop. So how do I find my velocity from this?
The square root of the derivative of both components squared, kind of, and that's sum.
Yeah, well, I'm going to go slightly slow. So I'm just finding my velocity, and then I'll find my speed. Okay, so I take the derivative of t cubed, which is 3t squared, in the I hat direction plus 2t in the j hat direction. That's my velocity. But what I'm needing here is my speed. So I need this, which is okay, so remember, if I'm finding the length of that thing, I square the components and then take the root. So I have 9t to the 4 plus 4t squared, all rooted. Alright, and then finally, I know...
How would I see that I need the speed?
Sorry?
How would I see that I need the speed here, and not just the velocity?
Because we've just talked about when you calculate, you want to find the length of the curve, so you need the speed along the curve, and you integrate that to get the distance. Yeah. Okay. So this tells us that our little arc length element is okay. So this says if you move for a very small delta t, the amount of ds that you get is this. Alright, so now we take our curve, and it is going to be the integral from a to b of our speed. And let me just add in another page. Alright, so I'm going from, where are we going? Thank you, -1 to 2 of this thing. Another way to think about it is you've done a kind of a change of variables. You've gone from ds here to dt here. Okay? And you can practice your integration. You can do things like, so this is worth thinking a little bit about how you would integrate this. I will write out the full solution, but practice your integration. If you end up with this, you will end up with So suppose you did the work and you ended up here. How would you reality check this?
Take the derivative and just check if it's Z.
So I mean, this is a number. You can't take a derivative. I mean, it's going to be 0. So this is, I've just said, okay, the length of the distance my little fly traveled is this. How can you reality check this? What is the first thing you know about a distance? Positive. Okay, so I would plug it into your calculator and check that it's positive. Okay. And that's probably the easiest and quickest reality check you need to do. So because we are dealing with the speed, we're dealing with a positive quantity, you need to end up with something positive. Okay. Work through this in detail. I will put up the full solution in these notes. Okay. Alright, and you can read about this, but you could parameterize in terms of theta. And if you're going to be in 3 dimensions, you might parameterize in terms of theta and phi. You might, in fact, end up parameterizing in terms of the radius and theta and phi. So these are all just, I mean, it sounds initially like, why would you want to do that? But it actually makes your life a lot easier, particularly when you're in electromagnetism and you're dealing with spherically symmetric systems. You really don't want to be working in X, Y, and Z. You want to be working in things that help you make use of that symmetry. So you can check for yourself that this is correct. All right, so let me pause for a moment and ask questions about parametrization. Okay, so we will carry on working from the worksheets from last week a little bit today, and I suggest that you kind of just keep practicing with it. It is just something, it's a new skill you need to learn. And initially it might feel weird, but it will get better. So, that was what we've just been dealing with, is the idea of curves in space. So we're thinking of a situation where we have one of our good old function machines, we put in a time, we get out a vector. Okay, but I'm sure you'll be delighted to know that there are many more things that we can do with function machines. For example, what we're going to do today is now we're thinking about, instead of putting in a single number, we're thinking about putting a single point into our function machine, and we're going to get out a value, an f of x, y, z. Okay. Why might we want to do that? Well, a good example would be if you want to create a map of the temperature of various places in the world. You're going to create a function which takes in a location, and a location is really an x, y, and a z, and it spits out a number, which is the temperature. So that's the kind of thing that we're thinking about. We're mapping, for example, positions to temperatures, positions to, okay, I can't think right now, but other things. Okay, so our formal definition here is a function of n real variables. So we're just going like straight for the big kahuna. We're thinking n here. Usually for us it'll be 2 or 3, but everything we do is generalizable beyond that. Okay, so it's a rule that takes a point at x1, x2 up to xn, and it spits out a unique real number. So it's still being a function in that you put in something, and that something that you put in only gives you one output. It doesn't give you 2 possible outputs. Okay, so it's not doing anything particularly weird. We've just changed what it is that we're putting in to get our output. Okay, and as you might expect, the set of real numbers that, well, the points that we put in is called the domain. The set of real numbers that we get out is our range. And you can read through that. It just makes, we're just really saying here, the domain convention says just pick the largest set of points for your domain that makes sense. don't try and be picky. Which basically means think of your domain as kind of Euclidean space, so all x, y, and z, unless we're explicitly restricting it to, I don't know, lie on a sphere or something like that. Okay, so let's think. All right, so now we need to work through the usual process that we work through when we're learning about a new kind of function. What do they look like? How do we graph them? Then we're going to talk about derivatives and so on. All right, so function of one variable, straightforward. Okay, you plot your independent on the x, you plot your dependent on the y, and you get a curve. Hurrah. Okay, we've done this a lot. We've just seen a slightly different thing where we couldn't plot our independent variable on the same axes. Okay, that was our parameterization and stuff. But here, now we're actually going back to thinking like this. So we're going to plot, for example, a function of two variables. We've got our two independent variables on the axis here, and we plot our result, and we get a surface usually. Okay? Good luck with plotting functions of three variables on a two-dimensional page. If you manage, that'd be great. So most of the examples we'll do, just because we want to build up a visual intuition here, is we will be looking at functions of two variables, because then at least we can plot the wretched things. Okay. But once you've built up that intuition, you can use that intuition when you're thinking about things in higher dimensions. All right. So how do we go about plotting things? Well, we could plot like we've just seen in the surface. So we can plot things like this, but that is really quite tricky to draw. So an option that we have for plotting, okay, that is mine. Okay, 45-minute break. I will just tell you about level curves and then we'll actually take a break. Level curves, you've probably actually seen a lot of level curves out in the wild. For example, if you're wanting to have a graph, if you're wanting to have a map that tells you about the heights of things, you can't actually have a 3D map, so what do? You make a contour. How do you make a contour map? You basically imagine slicing your three-dimensional space, and at each slice you just map out what the intersection of that plane and your surface looks like, and then you put it all in a delightful map like so. So that is exactly what we do with level curves. Essentially what we do is you take your surface and you decide, so up on the z-axis are the different values that the dependent variable takes. So you pick different values of the dependent variable, for example 20. So you fix z is equal to 20. So it's like you put a plane across at z is equal to 20 and you map out that intersection. So here is when z is equal to 20, that's what we get. If I let z equal to 35, then I get that. And you can build up a picture. Okay. Here are more level curves that you've probably seen in the wild. Average air temperature near sea level in July in Fahrenheit. Here we have rainfall. So these are all, use your intuition. Okay, this is nothing new. It's stuff you already know. Okay, so I was going to ask this as a question, but I just missed it. If you think about it, what you're doing with a level curve, you've got a surface, and you fix a height, and you think about what happens when you intersect a plane with that surface, and you get a curve. Now imagine that you've got a three-dimensional thing, so you've got an object. What is the equivalent going to be? What would you fix in order to be able to imagine? Yep.
I guess you can see it as coloring the points on the surface.
You can think of coloring the points, and then, but what you can do is, if you want to kind of have the equivalent of level curves, you fix values of your dependent variable, So now we're thinking of a function of 3 variables. You put in an x, y, and a z, and you get out some other thing. Now if I fix values of this, I'm going to end up with something in 3 dimensions, which is a surface. So if you have a 2-dimensional surface, it has level curves. If you have a 3-dimensional object, it has level surfaces. Okay. Okay, let's think about what this looks like. All right, here is here's a function of 3 variables, and I bet you can tell me what it is.
Sphere.
Kind of a sphere. It's a hypersphere because it lives. So the final value. So we put in an x and a y and a z, and we square it, and we get something else out. So it's kind of a hypersphere.
What's the difference between a sphere and a hypersphere?
A dimension. So a sphere is just living like this, but a hypersphere is actually living in the space I can't even do with my hands. Okay, but if I now remember what we do with level curves, we set the dependent variable. We make it a constant, and we look at what we get. Well, here, if I make this my dependent variable constant, then what do I end up with? I end up with a sphere. That is my level surface. So that's kind of giving me my cross-section of my weird 4-dimensional space. Yeah, okay. So this would be one of the ways that you can start to kind of visualize things in 4 dimensions, which is just a bit, yeah.
So a 4-dimensional map, a 3-dimensional object is the same as a 2-dimensional object is to a 3-dimensional map.
Yeah.
You can also go in 5, 6,
Yep.
7.
Yep.
Higher.
I mean, you can keep going, and you can also go down. So a point is the same to a line as a line is to a surface. And you can, but I don't know what we call the things up here. I mean, once we get up here, they're just hyper. They're hyperplanes, they're just, yeah. Okay.
What happens if you go like below the 0 dimensions?
Ooh, tricksy.
Negative
I like it.
dimensions.
I don't know.
And the negative
That is a stretch goal for you to work on this week. You're welcome.
Yeah, I don't know. There's a concept that's used.
All right. So please spend a little bit of time. I will give you questions in the online quiz to just kind of think about surfaces, level curves and stuff. This is just familiarization stuff. But we will need to think about rates of change, because of course we do. Why else would we be doing this if we didn't want to think about derivatives? So let's just take like a 2-minute break. Stand up, drink something, chat, and then we will get back to this, and I will just check that the recording is happening.
You know what's also fun? Buying a
Really different answer.
Ja. Volgens mij kunnen ze hier wel erbij.
Okay,